Hi guys, in today's video we're going to be looking at Newton's law of gravitation, and particularly we'll be looking at the apparent weight of an object. So we want to start by recalling that objects which are on the surface of the Earth are not technically in a truly inertial frame of reference, and the reason is the Earth itself is actually rotating through space. So today we're going to look at the effects of that rotation. And normally this effect is very small, and so we can ignore it, but today we'll be focusing on that effect. So we're really going to be dealing with a planet, and I'm going to call this just Earth for lack of a better name. And this planet is rotating about its axis. And so we can recall from class that when we're at the poles, we don't really feel much of a difference. There really is no effect from this rotation. But as we travel outwards from the poles towards the equator, we can start to feel some effects. It's still very small, but today we're going to pay attention to it. So we'll go ahead and look at a person who's standing here on the equator. And what we want to recall is that when we are, for instance, on the equator or anywhere else that is not at the pole, the true weight of this person is not going to be equal to the force of gravitation. And so in this case, we're going to go ahead and define our term here, which is going to be the true weight we'll call as weight W naught. And that is just going to be equal to our gravitational force from the Earth. So from Newton's law of gravitation, that will be this right here, which is to say mass of the Earth and the mass of the person divided by radius of the Earth squared times g. So this is just Newton's law of gravitation. And this is what we call the true weight. So if we look at this person standing here, let's say they're standing on a scale. This person is going to have some true weight pulling them towards the center of the Earth. That's just the gravitational force. And then the scale itself is going to exert some force outwards. And so one thing we want to take into account now is we're going to think we're sitting in space somewhere. So our reference frame is space, and we see that this Earth is actually rotating around. So the person here standing on the edge of the Earth is actually going to be rotating with the Earth now. So that's to say we actually need to have some sort of a radial force pointing inward to cause this circular motion. So we've dealt with this scenario before. We have forces and a radial force. So basically we're going to go ahead and say we know in this instance, the true weight then minus the force of the scale must give us our m person v squared over r term. So this is our condition for circular motion. And we'll go ahead and note the force that the scale reads is really going to be what we call apparent weight. And so what we can do then is rearrange this, and we should see that our apparent weight at the equator is going to be the true weight minus this mv squared over r term. And this is sort of the relation which we are going to want to use today. And this sort of just gives us a relation, and again it tells us if we are at the equator, our apparent weight and our true weight are not exactly equal anymore. And so we have some extra term from this rotation that we're now taking into account. And I want to be clear here, this is true only at the equator. So real quick before we move on, this is going to change if we're, for instance, some other position up here between the equator and the pole. And the reason is here, our true weight vector, which points towards the center of the Earth, is not going to be aligned with our radial force vector. So this here will become some sort of a vector equation, and things will get more complicated. Okay, so let's go ahead and read the problem statement for today, and that is as follows. Planet X rotates in the same manner as the Earth around an axis through its north and south poles, and is perfectly spherical. An astronaut who weighs 943 newtons on Earth weighs 915 newtons at the north pole of planet X and only 850 newtons at its equator. The distance from the north pole to the equator is 18,850 kilometers, measured along the surface of planet X. How long is the day on planet X? At this point, you should pause the video, reread this problem a couple times, and maybe even try it on your own. Okay, so we're given a lot of information here, and I've sort of distilled down a couple of the things that we're given here. Basically, we're given the weight of the astronaut on Earth, and then we're given the weight of the astronaut on planet X at the pole and at the equator. So one thing we first want to note then is we have the true weight of the astronaut both on Earth and on planet X. And the reason is the apparent weight is equal to the true weight at each of the poles of a rotating a planet. So that's to say we're given really that the true weight on Earth is equal to 943 newtons. And then we're given the true weight on planet X is equal to 915 newtons. So this is something we should initially write. And I'm going to write all of our true weights in green and then our apparent, or our weight at the equator in red, just so we sort of have some distinction between the two. So here right away we see we're given a lot of information about our true weights. And so what we can do right away is we can go ahead and solve our true weight on Earth to find the mass of the astronaut. And that'll be the same on any planet. That's just the astronaut's mass. And so here we know the true weight is just going to be equal to the mass of the astronaut times our g. And so again, this astronaut is on Earth, and so we assume that g is relatively constant, and this really is just the weight of our astronaut. And this is something we've done a lot of times before. So what we can do then is just solve our equation here. We know g is 9.8, and so this should lead us to the mass of the astronaut, which is 96.2 kilograms. So we'll go ahead and utilize that a little bit later. This is all still dealing with the true weight on Earth. But now I'm going to jump over, and real quick I'm just going to note that we're also given something about the circumference of planet X. So we're told that this distance here along the surface is equal to 18,850 meters. And so what we can do there is we can go ahead and use that to find the radius of planet X. So that's to say we're given a quarter of the circumference of this planet. So basically 1/4 of 2 pi times the radius of X is equal to 18,850. So we can go ahead and solve this directly for the radius of planet X. And this is something we'll need. So the radius of planet X then we get is equal to 1.2 times 10 to the 7 meters. So this is another piece of information we're going to use here. And in this problem, as you'll see, sort of we're going to really just work our way through what we know and what we can solve for. And eventually we should hopefully get to the period of rotation, which is 1 day. So here we have our radius. So we can keep working on the true weights. We still haven't done that for planet X. So if we go back, we know the true weight for planet X is going to be equal to, in general, g times the mass of planet X times the mass of the astronaut divided by the radius of planet X squared. And so we can now sort of impose all of the things we know on this equation. So we know the true weight of planet X, we know g, and we now know the mass of the astronaut and the radius of planet X. So from here we can get to the mass of planet X. And we should get the mass of planet X is 2.05 times 10 to the 25 kilograms. So now we have the mass of the planet and the mass of the astronaut. And so the only piece of information we have not used now is this weight at the equator. So now we want to go ahead and recall our equation from before, which basically told us that the apparent weight of an object is going to be equal to the true weight, so this is in green, true weight, minus our term mv squared over r. So in this case, this should be the mass of the astronaut, because the astronaut is the object standing at the surface of the Earth, of the planet, and the radius of planet X. So here is now another condition which we can impose on our system. So our weight apparent, we know at the equator, we are given that the weight apparent is equal to, and let me just write this over here so we recall, we're given that the weight apparent at the equator is 850 newtons, and this is from the problem. So we can go ahead and just set this equal. 850 is equal to the weight, and this should be the weight of x naught. So that's to say the true weight of the astronaut on planet X is 915. And now we have the mass and the radius of the astronaut as well. So we can now go ahead and solve this term. And we see the only unknown we have here is our velocity. So this relationship here, we plug in our mass and our radius, and we can get to a velocity. And before actually solving for that velocity, let's go ahead and recall, once we have our velocity, we can really get directly to the period. So in this problem, we're really looking for how long a day is, which is to say we're looking for the period of rotation of this object. And so we'll recall then, the velocity of this object is going to be the distance it travels in one rotation, which is 2 pi r, so it goes around one circumference, divided by the time it takes to travel that distance, which will be 1 period. So we have our relation that the period is just equal to 2 pi r divided by the velocity at the surface. And so here is a relation from this condition right here. We can solve for velocity, plug that in here. This should be radius of x. And so once we plug that in here, we can solve directly for our period, and that's what this problem has asked us for. So we should go ahead and get that the period on this planet is 2.6 times 10 to the 4 seconds. And this is what we were asked for. So let's go ahead and recall how we got here. First, we used the true weight of the astronaut on Earth to find the astronaut's mass. Next, we used the true weight of the astronaut on planet X to solve directly for the mass of planet X. We recalled the relationship between apparent weight and true weight at the equator to solve for the velocity that planet X must experience at the equator. And finally, we used this velocity to solve for the period. Okay, so I hope this video was helpful, and I hope this helped you gain some insight into what can be a pretty tricky concept, which is the concept of apparent weight. So if you have any comments on this video or any of the videos here, please leave those on the link to the right of the video link. Thanks for watching.